Hi, welcome to my channel. This is Venky. Today I would like to share facts about cosmic relativity. We will start with the basics of relativity, the classical relativity, then move with the special theory of relativity, and then conclude with the general theory of relativity with some good illustrations. Let's begin with classical relativity first, something that we experience in everyday life. Imagine a moving truck, a truck moving, say, at a speed of 50 kilometers per hour. The truck, relative to outside environment, is in motion. Assume there are two travelers in the truck. The travelers in the truck are stationary objects, as both the travelers and the truck are moving at the same speed. Hence, with related to the truck, the travelers are stationary. And the laws of physics stay same inside the truck as they would on the ground with the travelers are standing still. Okay, we have a moving truck, we have travelers on the truck. Now assume that the travelers on the truck decide to play. No, they want to throw ball at each other. When they throw the ball, say at a speed of 10 kilometer speed per hour, they observe that the ball they are throwing is moving at the speed of 10 kilometers per hour. This is correct. Now let's add one more frame of reference. Let's imagine that an observer is watching this moving truck and the travelers are throwing ball at the truck. Now the observer is stationary. Relative to the observer, the travelers are moving at the same speed as the truck. Now, with reference to the travelers in the truck, the ball is moving at 10 kilometer speed, which is correct. With reference to the observer watching the truck, the ball is moving at 60 kilometers per hour. This is also correct because from an observer point of view, the speed includes the speed of the truck plus the speed of the ball. Both are right. So the conclusion from the classical theory of relativity is that there is no such thing called absolute motion. Objects move relative to each other. So it is vital that when you talk about speed, you always specify the reference. Let's quickly see one more example on classical theory of relativity, where I would like to bring in the aspect of speed once again because speed is the fundamental core that drives our next discussion on special theory of relativity. We all know that speed is nothing but the distance an object traveled divided by duration. In the previous example, we saw that speed is relative. That's the very basic feature of speed, that it is relative. Another basic feature of speed is that it is additive and subtractive. Let me try to explain this to a simple example. Now let's imagine we have two characters A and B playing the game of catch. Assume that A is throwing a ball at B, say at 5 meter per second. Now B feels that the ball is approaching at fast. She knows that if she moves away from the ball, she can bring down the speed of the ball. So A is throwing the ball at 5 meter per second. B decides to move. B is moving away at say 3 meters per second, which means the ball will approach B at 2 meter per second, 5 minus 3. Now assume that B decides to move towards the ball. A throws the ball at 5 meter per second. B is now moving towards the ball. So the ball will now approach B at 8 meter per second, which is 5 plus 3. So the conclusion is that speed is both additive as well as subtractive. You can change the speed of an object either by going towards it or going away from it. Let's talk a bit about the speed of light. We saw that the speed is relative, but still there is a profound mystery in all of science around the speed of light. The speed of light is constant. Let's think how Einstein came with this idea that the speed of light is constant. The principle of relativity does not hold good for the speed of light. Over the course of many centuries, many people struggled to understand light. In the 1600s to 1800s, a whole group of physicists spent a lot of time and effort in trying to measure the speed of light. With all those experiments, we now know that the speed of light is close to 3 lakh kilometer per second. So people understood the speed of light. Good. But still there was a profound mystery. We saw that speed is relative. We say that an object has this speed or that speed relative to this object or that object. But the question is, What is that thing relative to the speed of light? The answer didn't seem apparent. The puzzle remained. This is where the genius of Einstein comes into the story. Einstein had this uncanny capability of looking at something that people had been staring at. Einstein told that, look, if the equations are specifying that the speed of light is 3 lakh kilometer per second, but the equations don't specify what the speed is relative to. Maybe that's because you don't have to specify anything. So Einstein said that the speed of light is 3 lakh kilometer per second with reference to anything. So the conclusion according to Einstein is that speed of light has no relativity. Interesting. Now let me quickly give you a simple illustration to explain this. Now once again we have A and B out there. B now has a meter in her hand that can measure the speed of light. When B is standing still, A is throwing a laser beam at B. B measures it and says that it is 3 lakh kilometer per second. Now let's change things a bit. B decides to move away as A is throwing the laser beam of light at B. So A throws it at B and B decides to move away. Now you would imagine that as B moves away, the speed of light would come down. But no, Einstein says that the speed of light is always 3 lakh kilometer per second because it is constant. It is the law of nature that speed of light is that number relative to anything. Similarly, if B is running towards A, you would think that the speed of light would go up. But no, it's always 3 lakh kilometer per second again. So the conclusion is the principle of relativity does not hold good for the speed of light. There is no frame of reference for the speed of light. The reason I brought in speed of light is that this is the basis for the special theory of relativity, which we are going to discuss next. Okay, so we discussed the classical theory of relativity, saw that the speed of light has no relativity. All good. With this understanding, let's move on to the next topic of discussion, the special theory of relativity. We know that speed is space divided by time. We also know that speed is constant. So if speed is doing something weird by being constant, then space time should also be doing something weird. Let's see what is time dilation. Let's try to understand what time dilation is. We all know that clocks that are properly functioning tick off at the same rate. So they will all be sync with one another. Here's the thing. The constant nature of light speed says that all of that is wrong. It tells us properly functioning, properly set clocks do not generally agree with one another. Reason, speed, motion can affect time itself. Now this is the basis for special theory of relativity. The theory states that faster you travel through space, slower you travel through time. Interesting. Now let me give you a quick example. Imagine a person traveling in a spaceship close to the speed of light. According to this theory, he will travel slower through the passage of time relative to a person on Earth. Now, with reference to someone on Earth, what is 1 year for the person on the spaceship could be 50 years for the person on Earth. Now, this is reality. This is the effect of speed on time. Now, this is true not just with the normal mechanical clocks, but with the biological clocks as well. Interesting. Which means when you come back to Earth, you would have just crossed 1 year, whereas on Earth, time would have passed by 50 years. Now, this means you have moved through the passage of time slower as you move faster in space. Now, this is what is called time dilation. Let me try to explain how speed can dilate time. For this discussion, we need to measure the time. You can use any kind of clock, but I'm going to show a special kind of clock. It's a very powerful kind of clock for assessing the effect of motion on time. It's called the light clock. A light clock is a contraction in which we have two mirrors that are facing one another, and a ball of light will bounce in between them, as you can see in the picture. And every time the ball goes up and down, you can think of that as tick tock. Though this is an unfamiliar clock, but conceptually, a light clock is no different than any other kind of clock. It is easier to reach our conclusion using the light clock. It will be a bit difficult with other kinds of clock due to its complex internal mechanism. Because the tick tock mechanism is so simple in a light clock, we can easily use it to understand how motion affects the passage of time. Let's see why moving clocks tick slow. So imagine we now have one more light clock and is in motion. You can see two light clocks here. From your perspective, think about the trajectory that the light will travel in the moving clock. The red line shows this. From your perspective, the light will start here. From the top, it hits the bottom of the mirror here, and then again it goes to the top. It goes to the top. So from your perspective, the light would have undergone a diagonal up and a diagonal down trajectory since the clock is in motion. You can observe that the clocks are showing different time. The clock in motion records time slowly. So if the clock is moving, the time in the clock slows down. You can see that the time in the moving clock has actually slowed down than the clock that is actually stationary. So why is that the time in the moving clock slows down? Think about the trajectory of light in the moving clock. Because it is diagonal, the trajectory that it follows for a tick and tock is longer. That means light has to travel that extra distance to complete a second. This is what causes time dilation. The rate at which time elapses on a moving clock is slower than the rate at which time elapses on a stationary clock. And this is true with any kind of clock, and this is reality. So the conclusion is clocks that are moving relative to each other must tick off differently. And it all comes down to the speed of light being constant. Let me give you one more quick illustration how moving faster through space can dilate time. Right now, here I am. You would say that I'm not moving relative to you. But of course, I'm moving. My clock is ticking second after second after second, taking me forward in time. So I'm moving through time. Now imagine that I get up and start to walk. Einstein basically told that as I start moving, I divert some of my previous motion through time into this motion through space. So I move through time less quickly. But of course, time dilation takes effect only when you move close to the speed of light. But this idea, according to me, is the most straightforward, intuitive way to understand time dilation. Okay, finally, the general theory of relativity. We saw that speed affects the passage through time. There is something else that can also affect your movement through time. It is gravity. Around 11 years after the special theory of relativity, Einstein came up with the general theory of relativity, and the theory states that higher the gravity, slower you move through time. While Newton described what is gravity and gave us a formula to calculate gravity, he did not explain what causes gravity. Einstein came in and explained what causes gravity. Now look at this picture. Einstein said that space-time is actually like a fabric and mass can bend space. You can see Earth in this picture bending the space-time. According to Einstein, when mass bends space, then this is what is gravity. This is what causes gravity. Observe that the mass is causing a curvature in space-time. This curvature in space pulls other masses around like moon. It is the combination of inertia of the moon and the gravity of the earth that keeps moon in its orbit. So let's understand what time basically is. Time is a kind of series of moments, a series of snapshots, one moment after another moment after another moment. And any physical process can be described in this way: a flower or a horse running moment after moment after moment. It is just a series of snapshots that capture each subsequent moment. So let's imagine that this is the space-time grid. So a space-time grid is essentially the unfolding of one moment after another moment after another moment. In this picture, you can see several events happening: clock ticking, a cat jumping, a horse running, moment after moment after moment. The horizontal direction represents the space, and in the vertical direction, we have the unfolding of time. So, this is a simple illustration of space time. So, in this space time grid, as you can see, mass not only bends space but also distorts time. This is the basis for the general theory of relativity. This is the reason why time runs slower with higher gravity. More mass means more gravity, and more gravity distorts time and causes time to slow down. Okay, we started with the classical theory of relativity, then we saw the special theory of relativity, and then the general theory of relativity. All good. But the question that should be running in your mind is, okay, these theories are interesting, but are they true? If they are true, where are they being used? Good question. You must be knowing about the GPS satellites. There are 24 of them orbiting the Earth in 6 different orbits, with 4 of them in each orbit. We all know that these satellites are used in the navigational system to reach a location. These GPS satellites are around 20,000 kilometers away from the Earth. They also go around the Earth at a constant speed, and these carry an atomic clock in them. The time in these GPS satellites should be synchronized with the time in the GPS receiver. So, what's the relationship between GPS satellites and relativity? We saw in special theory of relativity that moving clocks tick slow. Also, in general theory of relativity, we saw that if you compare two clocks, the clock experiencing higher gravity will, will tick slow. These GPS satellites move at a speed of say 3.9 kilometer per second, and they are at an altitude of say around 20,000 kilometers from the ground. So the special theory of relativity is applicable here because of high speed, and due to its high altitude, gravity will be lesser. So the general theory of relativity is also applicable in these satellites. So if you apply the mathematical formula, then according to special theory of relativity, the clocks in the GPS will run slow by 7 milliseconds per day. As per the general theory of relativity, the atomic clocks in these satellites will run faster by 45 milliseconds per day. So overall, the clocks in the GPS satellites will run faster by 38 milliseconds per day. Now, if this time difference is not considered while launching these GPS satellites, if the satellites are launched just syncing it with the ground time, then after reaching the orbit, the clocks in the satellites will start running faster by 38 milliseconds per day. Now, this can result in losing the accuracy of up to 10 kilometers. So, GPS satellites is one real time good example where both the special theory of relativity and the general theory of relativity are applicable. If you find this video informative, please subscribe and hit the like button. Thank you.